Terminology: a sequence is a function with a domain that is the set of natural numbers. The terms of a sequence are the range of elements of the function and are a set of numbers in a particular order. The first term of the sequence is commonly denoted by a sub 1, the second term a sub 2, and so on and so forth, up to a sub n. So a sequence is really just a series of numbers. It's just a set of numbers. Finite sequence, that means it has an end, fixed number of terms. Infinite sequence means it goes on indefinitely. You'll notice the difference between these two sets that they gave us. 2, 4, 6, 8 closes. 2, 4, 6, 8 with an ellipsis. The little dot, dot, dot means it keeps going. So that's how you know that you have an infinite sequence there. You can an infinite sequence can be restricted to be a finite if you just restrict the domain. But just so you know the difference. All right, let's look at example 1. Standardized tests love sequences. Find the next 4 terms of the sequence. So you're looking for a pattern. You're going to use that pattern then to finish out the sequence, or at least the next 4 terms in the sequence like they ask. So they have 2, 7, 12, 17. What is your pattern? Yeah, they're adding 5. And so if I wanted to finish this out, what would I do?
Add 5.
Just add 5. So my next terms would be 22, add 5, add 5, add 5, right? The next one, 2, 5, 10, 17, 26.
Subtract. So as you go. So take the.
Looks like we're going up by odds potentially here, right? So 2 to 5 is 5 to 10. Right. So what's your assumption there?
12.
So we're going to add, we're going up by odds. We're going to add 11. So we would have 37. Then we're going to add 13, right? So it would be, then we're going to add 15. And then we're going to add 17. Right? Next one. Find the first 4 terms of the sequence given by a sub n equals 2n negative 1 to the n. All right, if they want the first 4 terms, and the first term is a sub 1, and they have given it this way, then we would just plug in a 1. So if I wanted to find the first term here, the first term would be plugging a 1 in. 2 times 1 times negative 1 to the first power, all right? So my first term here would be negative 2. And then if I wanted to find my second term, I would just plug in a 2 there. And my second term would be 4. Third term. And then fourth term. All right, and so if they give it to you in this format where they actually give you a function here, then you can just plug it in to find your term number. And this leads us to our next term, which is explicit versus recursive formula. So the first 2, they gave you these and they wanted you to finish it out. The last one, they just told you how to find it. All right, so try guided practice 1 there. Guided practice 1, bottom of page 590. All right, so 1A. What's happening here? Dividing by 2. So if you kept going, you would 2, then 1, then 1/2, then 1/4. All right, or 0.5, 0.25. All right, what's happening on B? All right, so we're just adding by one more number. 1, then 2, then 3, then 4. And so your next 4 terms there would look like this: 29, 37, 46, and 56.
So how would you write that looking at 8?
All right, this last one, they gave us the formula for it. So you just had to plug in your numbers. So your first 4 would look like this: negative 9, negative 2, 17, and 54. All right, top page 591, recursive and explicit. A sequence can be written in recursive or explicit form. Recursive form means that you must have the number in front of it to find the next number. okay? And so recursive will tell it to you in a format where it says the number in front of it plus this, or the number in front of it times this, okay? Explicit tells you you can pick any term out of the air, the 15th term, and you can plug a 15 into that formula and find that term, okay? So recursive requires the numbers in front of it. Explicit is all you need is the term number that they've given you, all right? And so here are two examples. It wants us to find the 5th term of each sequence. The first one, this would be an example of recursive, okay? The way that you know that I'm looking at recursive here is this guy right here, a sub n minus 1. That means the term in front of the term we're talking about, okay? If I'm talking about a sub n, then a sub n minus 1 means the guy in front of it, okay? And so when you see something like this, they've given you recursive form. And for this one, we need to start out with the first term, pretty much. The first term starts us out, and then we can go from there. All right, so if I have my first term is 1, then if I want to find my second term, let's say I want to do this, then this guy right here would be the first term, right? 2 minus 1 is 1. And then I'd say plus 2 times whatever term I'm on minus 1, right? And so if I'm doing this one and I know what my first term is, I can just plug it in there. And so to find my second term, I would say it's going to be the term in front of it, 2, plus 2 times what term I'm on, 2 minus 1. And so this would be 2 plus 4 minus 1, right? Which I'm going to get what here? 5. So that's my second term. And then if I want to find my third term, I'm going to do the same thing. I'm just going to take this where this goes. So I'm going to put 5 here plus 2 times 3 minus 1. So 5 plus 6 minus 1 is going to give me 10. That's my third term. To find my fourth term, I'm going to use this one, 10 plus 2 times 4 minus 1. So that's going to give me 17. And then to find my fifth term, which is the one I'm looking for, I'm going to say 17 plus 2 times 5 minus 1. So my fifth term here would be 26. 26. So that's how you would have to use recursive. You have to walk your way to whatever term you're on. Recursive requires you to just go step at a time. Unless you see some type of crazy pattern that you could just go in it. This one's not really an easy pattern because they have all these crazy, the term in front, plus 2 times whatever term you're on minus 1. So there's not an easy way to walk from one to the next. All right. Let's look at the next one. B. For B, they want the fifth term. In this case, they didn't require the term in front of it. All they require is what term you're talking about. And so for this one, to find my fifth term, I'm just going to plug in a 5. 5 squared plus 1, which gave me 26, all right? Which is the explicit formula for the same one, all right? 1 squared plus 1 was 2. That's my first term. 2 squared plus 1, that was 5. 3 squared plus 1, that was my third term. 4 squared plus 1, that was my fourth term. 5 squared plus 1 was my fifth term. All right. And so this was the recursive formula. And this was the explicit formula for the same exact sequence. Those were the same sequences. All right. So one's the So when you're this right here, just means the term in front of it. So if I'm looking for my second term, that's just where I'm going to put my first term. If I'm looking for my third term, that's where I'm going to put my second term. It just means the term in front of it. The example they've given us here with Fibonacci sequence. As a plant starts to grow, the stem has to grow for 2 months before it's strong enough to support branches. At the end of the second month, it sprouts a new branch. We'll continue to sprout one new branch each month. The new branches also each grow for 2 months, then start to sprout one new branch each month. If this pattern continues, how many branches will it have after 10 months, look at what they've given us here on the chart, which is actually on the next page. But this chart shows us month 1, they would have 1 branch, 2, 1 branch, 3, 2 branches, 4, 3 branches, 5 branches. This right here is the pattern at which the branches add to the tree. Look at the pattern. This is Fibonacci sequence. And so the pattern happens even as branches are grown on the tree. So we talked about end behavior of functions in chapter 1, actually. And what we found is that sometimes functions go on indefinitely, infinitely, and sometimes they will go towards a specific number, all right? And so the term here that we're looking for, if a sequence has a limit such that the terms approach a unique number, then that is said to converge. If the sequence does not approach a specific number, then it diverges, all right? And so let's look at these 3 that they have given us. The first one, 12, 9, 6, 3. What is happening with this particular pattern here? How are we getting from one to the next? We are doing what? Yeah, we're subtracting 3. So if I subtract 3, you can do that indefinitely, right? I mean, you'll just keep getting lower and lower and lower. In fact, you're actually going towards negative infinity here is what's going to happen. All right? It is not going towards a specific number. It is going on indefinitely in the negative direction. All right? And so if something does that, that would be divergence. This would be said to diverge. It doesn't go towards a specific number. It goes on infinitely in a direction. All right. So this would be diverge, or a divergent series. All right. Or divergent sequence. Let's look at the next one. What is happening here? We are dividing by -2, right? -2. Now, this one seems to be bouncing back and forth, right? But it's actually moving towards something, all right? If I were to keep going and dividing by -2, it would be going towards what? Look at the graph that they've given us. It's easy to see on the graph. All right, so if you look here, we started out at +36, then -18, and +9, then -4.5, right? Back and forth here. So we're technically dividing by -2, but if I were to change that to multiplication, what would happen here? Multiply by what? Multiply by -1/2. Anytime you are multiplying a sequence, like say you're getting from one to the next by multiplication, if you are multiplying by a fraction, you're going to be moving towards a number. If you're multiplying by a fraction, it is going to converge on a number, all right? And so if you're multiplying by a whole number, it's not. It's going to be infinitely going into a direction. But if you're multiplying by a fraction, you are going to be moving towards a number, and you're going to be converging. And so this one will, and it will actually converge towards 0. Let's look at this last one. So this last one's a little bit different. If I were to plug in some numbers, and they've given it for us, we have a sub 1, right? And they told us that that is -0.2. A sub 2. If I went to a sub 3, I would get -0.231. And they go back and forth. This one is going back and forth as well. All right. But it's getting closer and closer. If you look all the way down to like a sub 11, we have -244 and 12.245. It's bouncing back and forth, and it's getting close and close and close to 1/4. The problem is, unlike the one before it, which was bouncing above and below 0, right, and getting closer to 0, the positive ones are getting to +1/4, and the negative ones are getting to -1/4, all right? And so this one is not really approaching the same thing. If I were to look at one column, the odds, then I would say, oh, it's approaching -1/4. But then when I look at the even ones, it's approaching +1/4. So it's approaching two different things. So think way back when we were doing limits. Remember, if we wanted an overall limit, it had to be approaching the same thing. If they were approaching two different things, we said it didn't have a limit, an overall limit. Y'all remember that? We looked at graphs, and that's what's happening here. While this one was bouncing back and forth between positive and negative, they were both approaching the same number. These are approaching two different numbers. My negatives are approaching one number and my positives are approaching a different number. So this one would also be divergent. This one would also be divergent. So we would have a divergent one here because it's going to infinity. Divergent here because it's approaching two different things. And this is convergent because they are approaching one number. All right, so if it's approaching a specific number, convergent. If it's not, it's going to be diverging. All right, so go ahead and try guided practice. See if you can see which ones are converging, which ones are diverging. All right, the first one, what are you doing? You're multiplying by 1/4, dividing by 1/4, dividing by 4, multiplying by 1/4. Remember I said if you are multiplying by a fraction, it's always going to be what? Convergent. So this one's convergent. All right, what's happening in the second one here? So from 9 to 13, what do you do? All right, and then 13 to 15, you're adding. 15 to 16. 16, you're adding. So you're adding half of what you were adding before. All right?
Tricky.
So are you moving towards a number? No, you're constantly increasing here. Granted, by not much when you get to the higher terms, but you're constantly increasing. So this one is going to be divergent. All right? Let's look at this last one. My first term is going to be 3 times negative 1, right? My second term is going to be 3 times positive 1. My third term is going to be, my fourth term is going to be. What's the problem here? It's not going anywhere. So this one is also what? Divergent.
Good movie series.
We've been talking about sequences. Sequences are just the sets of numbers. Series is what happens when you add up the numbers. So if you have a sequence and you add it up, it is a series. Again, you can have finite and infinite series. Just because it's infinite doesn't mean it's necessarily, you can't add it up. For finite, obviously, you can always add them up. The sum of the first set of terms, 5 terms, first 6 terms, first whatever terms, n terms, is called the nth partial sum. So what they're doing here is they're giving you a series and they're saying, I only want a certain number of them added up. And the notation here is S sub n. So it's your summation of n terms. And you calculate it by literally adding the first however many terms they want up. All right, let's look at the example. Find the fourth partial sum of a sub n equals negative 2 to the n plus 3. So if they want the fourth partial sum, they want the first 4 terms. So you would say the first term, negative 2 to the 1 plus 3, or 1. The second term, negative 2 squared plus 3, 7. The third term, negative 2 cubed plus 3 is negative 5. And the fourth term, negative 2 to the fourth plus 3 is 19. If you want the fourth partial sum, you are literally going to add these up. And so when you add them up, you will get 22. All right? 22. So this would be the fourth partial sum of that. All right, look at the next one. Yeah, the next one, they want S sub 3. So they've just written the notation for you. That means they want the first 3 terms. So we said a sub 1 would be 4 over 10 to the first power, or 0.4. A sub 2 would be 4 over 10 to the second power, or 0.04. A sub 3 would be 4 over 10 to the third power, 0.004. So if I added all of those up, I would get 0.444. Easy enough. That's series are often and more conveniently notated using the uppercase Greek letter sigma. Sigma. If you have ever used Excel, this is actually the summation for Excel. So if you're in an Excel spreadsheet and you have a column of numbers, You can go to the bottom of that, click this little symbol at the top of your Excel, and it adds up all of the numbers in the column, summation. All right, sigma notation. And so it basically means add all the numbers in this series that I'm giving you. All right, and so this is the notation for it. If you see this notation, that is simply saying add it up. Add up the numbers, all right? The starting number, they tell you which term to start with. That's at the bottom. N equals 1. The top term, K, tells you how many, what term to end with. And then the A sub N, that tells you your explicit formula for that particular series, all right? So they give you the explicit formula, they tell you the starting term and the ending term, and they want you to add everything from the starting to the ending term, all right? They are called the lower bound and the upper bound, by the way. Lower bound and upper bound, meaning that where you start and where you end. And then N meaning the index. So that is the index of the summation. So whatever term you're on. So let's look at this example 6 here. Find each sum. So this is they want me to start for this first one with the first term. They want me end with the 5th term, and they've told me how to find all the terms. So if I were going to do this one, I would do my first term, 4 times 1, which is 4, minus 3, 1. My first term is 1, plus my second term. 4 times 2 minus 3, that's 8 minus 3, 5. My third term is going to be 4 times 3 minus 3 is 9. I'm writing, sorry. So 9, 4 times 4 minus 3, and then 4 times 5 minus 3. And so what they're wanting me to do is they're wanting me to add all those up. All right, that's all the summation means. Just because it goes to infinity doesn't mean you can't add them all up, because you can see how it is converging on something. If you look at this one, you actually end up getting this guy right here, all right? Anytime you have a repeating number, 0.7 repeating, it's always over 9. So 0.7 repeating would be 7/9. If it was 0.78 repeating, it would be 78 over 99. That's just how it works with repeating numbers. And so if you can see, like on the one we did, 0.44444, that would be 4/9 is what it's converging to. That's what it would actually add up to. And so that's how you can do it for infinite series as well. Just because it's infinite does not mean it cannot add up.